let's see. Let me fix my screen so I can see everyone. There. Okay. All right. All right, so we started talking about imaging systems the week before last. And when we talked about the phosphor plate, the PSP plate, how did we classify that detector? Did we classify it as a direct detector or indirect detector?
Direct?
Pardon?
Was it direct?
Direct?
Put an IN in front of that.
Direct definer?
I'll give you two choices.
So it's an indirect detector. The phosphor plate, what will happen is the x-rays will come in and will ionize the barium fluorohalide. So electrons will be released. And by the way, those electrons, when they're released, what material is it that will trap those electrons? Because that's our image data. So what in that phosphor plate will trap those electrons? What material is that?
Barium fluorohalide with europium.
Okay, so specific. Okay, so which one is it barium fluorohalide or the europium that's trapping those electrons?
Europium.
The europium, right? Because the x-rays come in and will ionize the barium fluorohalide, so the electrons get released, because ionizations take place, and then the europium that is mixed in with those phosphor crystals will trap those electrons and it'll hold them in a high energy state, because we don't want those electrons to drop back down and recombine with the barium fluorohalide atoms. Otherwise, we lose our image. Our image would be gone. So we do have electrons, but the game isn't over yet. Those electrons, yes, that's our image data, but we have to be able to process that image. We have to have that image detector release that image data. So what happens is you take that phosphor plate and you put it into the reader device, and then that laser will scan the plate. And when the laser scans the plate, that's when the electrons that are trapped in that europium get released from that europium. So they rise up out of the traps. And then as those electrons lose energy and drop back down to recombine with the barium fluorohalide, those electrons give up energy because, you have conservation of energy. So as the electrons lose energy, that energy is given up in the form of light. So that's why the phosphor plate is considered to be an indirect detector, because we do have light involved in the process here. So that light that is given off by that phosphor plate in the reader will be collected by what device? What will collect that light? Because that's our image data.
The photomultiplier tube thing.
That will be at the very end. So the light, when it's given off by the plate, gets collected by it's two words, and the first word is light.
Light guide?
Yeah, the light guide. Exactly. So the light guide, it's made of fiber optics. It will collect that light, and then it sends the light to a photomultiplier tube, and that's where the light will get converted back into electrons. And those electrons, that's our image data, and that's what we call an electronic signal. Okay. So that's why the PSP plate is indirect, because we go from X-rays, and yes, we do go to electrons, but then we also have light involved. And the fact that there is light in the process makes it an indirect detector. And then ultimately, at the end, we do end up with electrons, and that's our image data. Okay. So you okay with that? Okay, you could trace those steps or also list the composition of the detector. Be okay? All right. So then what that brings us to is the second type of detector, and it's called an FPD, or flat panel detector. And it has a thin film transistor technology involved with it. And we'll just take, a brief look and overview of what this detector looks like. We won't be going into extreme detail with the electronics. We won't be talking about voltages and gates and that type of thing. We'll just kind of do an overview so you have a basic understanding of how this type of detector works. So when you look at a flat panel detector, like the one that we have down in the lab that I have in the battery charger, if we were to take the covering off of that detector, this is what it would look like. So we'd have all electronics, and this would be a protective coating, and then underneath we would see some semiconductor material as well as more electronics. So it's all electronics, and that's one reason why if you drop it and it breaks, it's very expensive. With our PSP plate inside of that cassette, if we drop that cassette, you of course don't want to do that, but if we drop the cassette and the cassette breaks, maybe it's a couple $100 to replace the cassette because maybe the latch or something like that would break. But when it comes to these flat panel detectors, if you drop it, it can damage the entire detector, and there's no fixing it. It's one of those things that you just simply have to replace it. And then you're talking thousands and thousands of dollars, $70,000, $80,000, $90,000 or so for these detectors. So when it comes to the flat panel detectors, we do have two types. We have a direct one and we have an indirect one. So if it's a direct flat panel detector, that means X-rays will get converted directly to electrons. If it's indirect, then that means we have light. So anytime you have an indirect detector, we have light. And I would always remember it because of the eyes. Indirect has eyes in it, light has an eye in it. So if I have an indirect flat panel detector, I know that there's going to be light involved. Ultimately, though, we will end up with electrons just like we do up here. So just as an example, this is a protective casing for a flat panel detector for this particular corporation here. And if you pull the flat panel detector out, this is what this one happens to look like. And you can see that there are electronics up here. And then this is a protective coating. And if we could peel away that protective coating and look at just a small area and magnify it, this is what it would look like. So we're pulling out just a very tiny area. If you remember when we talked about image data characteristics, we said that detectors and images are made up of millions of pixels. So these detectors have millions of these little pixels in them. So of course, this is just greatly magnified here. This is as if you were looking at a cross section of it. If we were to take this image and then turn it, put it flat on its back, this would be like a cross section of that. And then if you were to look at a cross section in a little more detail, this is what it looks like, how we've got electrodes on the top, and then we've got an electrode down here. We've got something called amorphous selenium, which is a semiconductor material. And then underneath, we have electronics. Because I told you, if you peel away this protective layer, you'll have semiconductor material, and you'll also have electronics. And the electronic segment that is associated with this flat panel detector is referred to as a thin film transistor. You don't need to know exactly how the TFT works, but anytime you hear flat panel detector, then you just need to know that it's electronic and it's a thin film transistor technology that is associated with it. We will talk just a little bit about it, but we're not going to go into the details about how the voltages get applied and that type of thing. And it is layered on a piece of glass. This is why these flat panel detectors, one reason why they're so sensitive to dropping, because that whole detector on the bottom side is a layer of glass. So that's why, one reason why if you drop it, it is extremely likely to break. So one reason is because of the glass, and then the other reason is because of all of the small little electronics that are associated with it. So when you look at it in simplicity here, this light gray area, all these light gray areas represent the semiconductor material. So I told you, if you peel away the protective layer, you'll see semiconductor material. And then up in the corner here, these little devices, that's what represents the thin film transistor technology. It does run underneath the semiconductor material, but then it also appears up in the corner of each one of these little square areas. So just to kind of give you an idea as to what this looks like. So what do you need to know as far as this detector is concerned? Well, you do need to know that what we call the thin film transistor array, that's the the electronics. It consists of little individual detector elements layered on glass. So, I just showed you in that previous diagram that the glass substrate is the bottom layer, and then you have a layer of electronics. And then on top of those electronics, you have an active area or semiconductor material. And that active area, that's what you see outlined in green here. That is the semiconductor material, and its role is to capture the image. So the X-rays will interact with that semiconductor material. The other thing is, I told you that thin film transistor, it runs across the whole bottom of this detector, but then it also appears in the upside or the upper corner of each one of those little squares. So we have electrical components here, and the electrical components are involved with storing the data and then releasing the data at the appropriate time. So we'll be talking a little bit more about this. So when you look at this square in its entirety, like you see here in yellow, this is what we refer to as a DEL, and DEL stands for detector element. So flat panel detectors, or FPDs, they have what we call DELs, detector element, and they are physical dimensions, and you'll notice that they are in the shape of a square. Those are physical dimensions, and we have mentioned before that manufacturers can make these DELs to be different sizes in order to yield different levels of resolution depending upon where the detector is going to be used. And we're talking about these things being incredibly small. We're talking about micrometers as far as size is concerned, because you've got millions of them in a detector, so they have to be extremely small. So we're talking about micrometers. But the DEL, which is a pixel, is a physical dimension. So this is the DEL, and the DEL consists of an active area, and then it consists of electrical components. So the active area is semiconductor material. The electrical components is part of this thin film transistor network. You okay so far? Okay. So,
I have a question.
yes.
So you're saying that the DEL is the actual pixel and it's made up of those materials?
The DEL is a square. It's a pixel, but when it comes to flat panel detectors, it's referred to as a DEL or detector element as opposed to calling it a pixel, but yet it is a pixel. But you do need to know that square, that detector element, is referred to as a DEL. And the DEL consists of an active area and then an electrical component area. So every DEL has an active area, which is the light gray, and then it has a little electrical component area that, of course, runs underneath, but then will also occupy the top corner of those DELs. So the DEL is the square in its entirety, the pixel in its entirety. And these are the two components that make up the DEL. Does that help you? Okay. Okay. So, I told you all there are two types of flat panel detectors. We have indirect and we have direct. So the first one that we'll look at is direct. So if it's direct, remember, X-rays get converted directly to electrons. So there's no light in the process. So in terms of the composition of this, the DEL, as far as the active layer is concerned, the DEL is made of amorphous selenium. And you do need to know how to spell amorphous selenium. And this is how it's abbreviated. So this is the semiconductor material for a direct flat panel detector. And remember, direct means X-rays get converted directly to electrons. And the way I remember selenium is selenium has E's in it. Electrons has E's in it as well. So selenium, amorphous selenium, will convert X-rays directly to electrons. So what the amorphous selenium will do is it will absorb the X-rays, because that's the active layer. So it'll absorb the X-rays, and then it will convert those X-rays to electrons. And then in terms of the electrical components that exist in the detector are capacitors and thin film transistors. So here I'm throwing in a little extra piece here. Okay, the primary component that's composed of it are what we call thin film transistor, but the little piece up here in this upper corner consists of a capacitor as well as thin film transistor technology. So basically what happens is when the X-rays are converted to electrons, the electrons will migrate to the capacitors. So the capacitors are these little electrical components here. So a capacitor is a storage device. That's what a capacitor is. It's a storage device. And then what happens is at the appropriate time, those electrons that are in the capacitors in every corner of those DELs will be released. So all of the network of electronics underneath is the thin film transistor technology. And when voltages get applied to that network here, it basically signals to the capacitor, okay, release your charges. So the thin film transistors are responsible for releasing those charges, basically telling the capacitors, okay, it's time to release those charges. So the thin film transistors send a voltage to the capacitors and say, release the electrons. Okay, and like I said, we're not going to go into detail about exactly how that works, but that's what takes place. Okay, so you do need to know that the active layer is amorphous selenium and what it does. You need to know what the capacitor does, and you need to know what the thin film transistor is responsible for. And so when you look at it, and again, this is a significantly magnified image here just to show you what this looks like. We've got the remnant beam coming in. So, the X-rays leave the patient and they enter in, and we're not, we've got a protective layer and electrodes and all that, but, we're not going to go into detail with that stuff. What we're concerned with here is once the X-rays make it in to this active layer. So when the X-rays come in, this is amorphous selenium, and it will take those X-rays and end up converting those X-rays into electrons. So in other words, we've got ionizations that take place with the amorphous selenium, and so we get all of these electrons that are produced. And then the electrons in each DEL, because this is we're looking at cross section basically. This is a DEL, this is a DEL, DEL. So what happens is that those electrons will migrate to the little capacitor area, and they will remain there. Okay, they will remain there until it's time for them to leave the flat panel detector. Is he okay with that? Okay. It's a lot of memorizing, what does what. But again, with a flat panel, if it's direct, that means X-rays go directly to electrons. Electrons has E's in it, so does amorphous selenium. So, if you can perhaps remember it that way. Then we've got an indirect flat panel detector, and since it's indirect, we have light. And again, try to remember, light has an I in it, so does indirect. So X-rays go from light to electrons. And in terms of the composition, we have an extra layer on this type of detector. We have a layer that is referred to as a scintillator layer. Scintillator layer. The scintillator layer is going to be made of one of two things. It's either going to be cesium iodide, and you abbreviate cesium iodide like this, and you do need to be able to recognize the abbreviation for it. And it could also be composed of gadolinium oxysulfide. So it's either CSI or gadolinium oxysulfide. Okay. And what that scintillator layer will do is it will absorb the X-rays and it will convert the X-rays to light. And the way I would always remember this is scintillator has eyes in it, so does light. So the scintillator takes those X-rays and will convert X-rays to light. Then that light will interact with the active layer of the DEL, and the active layer of the DEL for an indirect flat panel is amorphous silicon. So it's amorphous silicon, and it's abbreviated as A-SI, so amorphous silicon. That silicon will take the light and convert it to electrons. And again, the way I would always keep these components in order and remember, what goes with indirect versus what goes with direct is I would think about the eyes, cesium iodide, X-rays to light, amorphous silicon. It's got eyes in it. It takes light and then converts it to electrons. So we have this intermediate, intermediate step here where X-rays get converted to light before they get converted to electrons. And then the same thing happens with the indirect as happened with the direct. Once we have those electrons, they will migrate to the capacitors, and those electrons will remain in the capacitors for each DEL and until it's time for those electrons to leave the detector. Okay? So you have to remember, indirect has a scintillator because those X-rays need to be converted to light. And then the amorphous silicon takes the light and will convert it to electrons. So this is what this looks like, all magnified here. The remnant beam comes in, and this scintillator layer, in this particular case, happens to be cesium iodide, and it kind of looks like this with these stripes here, and we'll see this in a second a little better. But that remnant beam comes in, and it interacts with the cesium iodide, and the cesium iodide will convert those X-rays to light photons. So these are X-rays, these are light photons, and those light photons will then travel to the active layer of the DEL, which is amorphous silicon, and the amorphous silicon will take that light and turn it into electrons. So the light will interact with the amorphous silicon, and it will turn into electrons, and then those electrons will settle into the capacitors. Okay. So we have an extra step here because this is indirect. The cesium iodide, you also need to know how it may be referred to. Cesium iodide may be referred to as a columnar or a structured scintillator. Columnar or structured. Okay, columnar or structured. And the reason is, when you look at cesium iodide, this is what it looks like. It looks like a column, and it is very structured. You may also hear it referred to as a needle phosphor because it looks like a needle. So either columnar, structured, or needle. And cesium iodide is artificially grown in labs. So it is grown to look like this. So what you're seeing here is just a graphic representation of this being the cesium iodide, these little needle phosphors, and then the active layer is down below here. Okay, so that's what you see there. So that's the cesium iodide, what it looks like. Do you have any questions up to this point? Y'all are quiet today.
I know you mentioned like or gadolinium oxysulfide. Is it still referred to as columnar structured, or does it have a different appearance?
Here's gadolinium.
There we go.
So there's your gadolinium. So you okay with the cesium iodide, knowing what that, or seeing what it looks like, how it does look like a column? If the detector doesn't consist of cesium iodide, then it consists of gadolinium oxysulfide. And it is referred to as a turbid or unstructured. Turbid or unstructured. If you notice, these phosphor crystals look like barium fluorohalide. I mean, basically, majority of crystals all look alike, okay, for the most part. But when it comes to cesium iodide, it's different. It actually is manufactured to look like a needle to a column. And there were reasons why that was done, and that's something that we don't have to go into anymore. But anyway, this is what gadolinium oxysulfide looks like. But it serves the same purpose. The X-ray will come in and it will interact with the gadolinium oxysulfide. And when it does, the gadolinium oxysulfide will absorb that X-ray and it will release light. Again, it's conservation of energy. So the light gets released, and then the light travels down to the active layer, which is amorphous silicon. And the amorphous silicon will absorb the light and will release electrons. And the electrons will settle in the capacitors within each DEL. So it's just a different type of scintillator, just a different type of scintillator. The gadolinium, just so you have a little idea about the history, the gadolinium oxysulfide was the first phosphor crystal that was used, but there was a decrease in spatial resolution with these types of detectors. Anytime you have phosphor crystals and phosphors release light, you get a spreading of the image. It can degrade structural edges. So then the cesium iodide came about and provided a sharper image, but now they're very comparable because of things that have been done in terms of the thickness of the phosphor layer and that type of thing. Our detector down in the lab, the one that's in the battery charger, our flat panel detector, it's made of gadolinium oxysulfide. So we have this type of scintillator layer, and we have amorphous silicon for the active layer. So that's what our detector happens to be. Okay. Oh, and by the way, let me mention to you too, I told you the thin film transistor, what's the base layer? What is the thin film transistor technology built onto? What's that base layer made of? And I told you that's why it could break. Yeah, it's made of glass. Okay. There are some vendors that are working with flat panel detectors that do not use glass. Glass was needed for the thin film transistor, but they've been able to work with other materials that won't impede the way the thin film transistor technology works, which is going to be something significant, because that will help the integrity of that detector and not be as likely to break if it drops. So that's something significant that the vendors are working on. So it's kind of neat to see that. And hopefully I'll learn a little bit more about that in November, because I told you about the big radiology conference in Chicago where 70, 80,000 people will attend. Of course, this year it's virtual, but I am going to do it virtually. And so looking forward to see what some of the vendors might have that's new out there. But I just wanted to mention that to you, is that this glass substrate at some point may end up being done away with. Okay, so you okay up to this point with the flat panel detector in terms of the two different flat panel detectors and how they acquire the charges? It's just, you're just going to have to memorize this stuff, look at it every night, or I guarantee you all of the materials and stuff will get switched around in your brain. It's something you just have to keep looking at. Okay, so now, we looked at image acquisition with the flat panels. Now we just need to look at image extraction. So we said, ultimately we end up with electrons. That's our image, okay? And those electrons, remember we said, they migrate to the capacitor and they remain in the capacitor. The capacitor stores those charges until it's time for that data to be released from the image detector. So what happens is the data will get extracted from each DEL, essentially in like a row and column manner. In other words, it's very organized in the way the data gets released from the flat panel detector. Okay, so it will release, it can release like a row at a time. It can go left to right, and then it comes down to this column or this row. So like the data will be released here, and then the data will file out here, data will file out here. So it's a very organized manner. Essentially, it's going basically from the top of the detector down to the bottom in a left to right pattern. And what happens is voltages get applied to the thin film transistors that run underneath, and it stimulates the capacitors to release those charges. So those charges will end up getting released. We'll come back, to that point, all right, a little bit later. So far with our PSP plate, we said how the photomultiplier tube will convert light to electrons, okay? With the flat panel detector, we said how we end up with electrons. The photomultiplier tube with the PSP plate, we'll talk about what happens with those electrons in the photomultiplier tube. And we will come back to this point with what happens to the electrons once they've been read out of the flat panel detector, okay? Because that's not the end of the story yet. We have to see what else happens to the charges. But for right now, we're just looking at the composition of the detectors and what's taking place, how these charges are acquired and extracted. Okay, but then we'll pick up from this point later on. All right, so do you think you can handle the PSP plate, the direct and the indirect flat panel? Maybe by Friday, right? By Friday? Okay. All right, let's talk about the charge coupled device, and then maybe we'll take a break. We'll do one or two more. Okay, charge coupled device. This is a CCD, and it is also referred to as an indirect detector. It's an indirect detector. Now, the CCD, it's a small little chip. It's like smaller than a credit card. It's just a tiny chip. It's very small. The CCD, what it does is it takes light and will convert it to electrons. Okay? So the CCD responds to light and will convert it to electrons. Well, what am I missing? What am I missing here? Yeah, X-rays. Because light doesn't come out of the X-ray tube, okay? But yet the CCD, it takes light and converts it to electrons. That's why this is considered to be an indirect detector. So, how does this work? So where does the light come from? Well, in terms of the CCD, there is a scintillator. Okay, there's a scintillator. such as cesium iodide. You know, we also talked about gadolinium oxysulfide when we talked about the flat panel detector, but in terms of the CCD, there is a scintillator layer that is made out of cesium iodide. And I shouldn't say in the CCD itself. It's actually, it can be attached to it or it can be separated from it. So there's scintillator material like cesium iodide that will take the X-rays and convert it to light. Then what happens is the light will get directed towards a CCD or towards multiple CCDs. And the way this is accomplished is the light will be directed either through a single lens or through multiple lenses or through fiber optics, via fiber optics. And so what this light does is once it gets to the CCD will take that light and will convert it to electrons. So we're going to look at a couple of different configurations here so that you can see, how this looks. And I think the neat thing is, I told you the CCD is smaller than a credit card, but notice here I told you that light could be directed just towards a single CCD. So you can have an image detector that only has one CCD in it. So how in the world can you X-ray anything with something that is smaller than a credit card? But it's just kind of neat, to think, who came up with all of this and how this works. So I'm going to show you a couple of examples here. So, of course, we're pretending our X-ray tube is over here. So we've got our X-ray tube, and the X-ray tube, releases those X-rays and, goes through the patient. We've got the remnant beam. So we've got a remnant beam that will interact with a scintillator layer. So there'll be cesium iodide. All right, there'll be cesium iodide somewhere in that imaging detector. And that cesium iodide will convert those X-rays into light photons. And then the light can go through a lens, and that lens will focus the light towards a CCD. One of the things about light is, and I don't know if you remember this when you've had some physics or whatever, but light is isotropic. Do you know what isotropic means by chance? Anybody remember what isotropic means? Isotropic means light, it spreads out in all directions. So if we have X-rays coming in and those X-rays get converted to light, we don't want that light just to fan out all over the place because then we lose our image data. So there's a lens in place, and that lens will focus the light to the CCD chip. Okay? The lens will focus the light to the CCD chip. Remember, X-rays can't be focused by a lens, right? X-rays cannot be focused by a lens. That's why we have to have a scintillator layer in here to convert X-rays to light, because then the light can be focused by a lens to the CCD chip. So this is what's referred to as a lens-coupled CCD. Now, some detectors, instead of having a lens, will have fiber optics. They'll have fiber optic tubes. Same thing though, X-rays come in, will interact with cesium iodide. Cesium iodide will convert those X-rays to light. The light is picked up by fiber optics and directed to the CCD chip. And so that's referred to as a fiber optic coupled CCD. Okay. This is exciting stuff, isn't it? I just think it's amazing how they come up, the technology, the science behind it. That individuals are sitting around thinking, how can we make these detectors? How can we improve these detectors? What materials can we use, for these? So I have my lens coupled and fiber optic coupled. So let me show you an example. This happened to be, the corporation was called IDC, and this was a CCD system. This was the first CCD detector, first CCD detector basically on the market for diagnostic imaging. And believe it or not, there is only one CCD chip in this detector. One CCD chip. And remember, how large is that CCD chip? Is it a 35 by 43 chip? It is the size, smaller than a credit card. But yet when you look at this detector, this is a 35 by 43 detector. So how in the world can you do a chest image and end up with something? Well, this is, kind of trying to did the best I could drawing this to represent what's in here. So the x-rays come in, the x-rays will come in the front of this detector here. So the x-rays come in, and right inside the front of this panel, there is a cesium iodide panel here, cesium iodide scintillator, that columnar scintillator. So the x-rays come in, interact with the cesium iodide, and light is released. Well, then where this angle is on this device, there is a mirror with a coating. We won't, you don't need to know what it's coated with, but it's coated with a substance that will take the light and reflect it up this direction. So it will reflect that light up towards the top of this device, and that light will go through this lens and be focused to this CCD. You don't need to worry here. This happened to be a 16 megapixel. You don't need to worry about that. But it got directed to that CCD. So you could capture a chest image on a CCD. So the reason this thing looks so funky and bulky like that is because you had to have a mirror to direct the light through the lens to the CCD. But this was the first CCD system that was on the market for diagnostic imaging. And it worked okay. There was some loss of spatial resolution though, because look how far away the cesium iodide panel is in relationship to the lens. So you've got all this distance, and anytime you increase your distance, there's a chance that you are going to have light photons that spread out a bit too much, and that degrades structural edges. The other thing too, because of the distance between the cesium iodide and the CCD, since you would lose some light photons, you may have to increase your mass a little more than what you would use with a flat panel detector, because you were losing some of that data. And so you'd have to increase your mass to make up for it. But nonetheless, it was the first attempt at having a CCD system. CCDs, just so you know the history, CCDs were first used in mammography. But they started in mammo. Okay. Why don't y'all take a break, and when you come back, then we'll look at the other CCD system.